Hello friends, so today we are going to solve questions from heat and thermodynamics, and we are going to solve the questions from all the questions will be from the mains only, and we are going to solve for 2017 two questions, 2018 also two questions, and from 2019 we are going to solve 15 questions. So in totality we are going to solve 19 questions. Okay, and all these 19 questions are from the mains only. So the first question, it was asked in the year 2017, and it states that an external pressure P is applied on the cube at 0 degrees centigrade so that it is equally compressed from all sides. K is the bulk modulus of the material of the cube and alpha is its coefficient of linear expansion. Suppose we want to bring the cube to its original size by heating. The temperature should be raised by. Okay. So in this case, obviously when we are going to press it, okay, there will be volumetric compression, and if you want to bring it to the original size, there should be a, you can say, thermal expansion, which is going to counteract this compression. Okay. And we have to use the relationship between the coefficient of volume expansion as well as the linear expansion, which is a quite standard format. So we are going to start with our, you can say, with the volumetric compression, and we know that the bulk modulus which is our K, it is given as negative of pressure P, change in volume, and divided by original volume. Okay. Or from here we can write that relative volume compression, relative volume compression, which is nothing but the ratio of change in volume, original volume, is equal to minus and P upon K. Now we want to restore it to original volume. So we can say that to restore the original volume, thermal expansion must counteract this compression. And along with this, we are going to also use the formula, that is our gamma volumetric expansion is approximately equal to 3 times alpha, which is our you can say linear expansion. Therefore we can write that volume expansion due to temperature increase volume expansion due to temperature increase, that will be our change in volume. Original volume is equal to our volumetric expansion multiplied by delta T, or we can write this as 3 times alpha delta T. Now this will be our, so relative compression should be balanced by the corresponding increase. Okay. Therefore we can say that equating compression and expansion, expansion, we get P upon K is equal to 3 alpha delta T, and from here we can say that our delta T will be equal to P upon 3K times alpha. So this should be our raise in temperature. Okay. So we get P upon 3K alpha. Option D is correct. D is correct. Next question. It was also asked in the 2017 means. It states that the temperature of an open room of volume 30 meter cube increases from 70 degrees centigrade to 27 degrees centigrade due to sunshine. The atmospheric pressure in the room remains 1 into 10 to the power 5 Pascal. If Ni and Nf are the number of molecules in the room before and after heating, then Nf minus Ni will be equal to. Okay. And in this case, there is change in temperature and the pressure as well as volume is constant. So therefore we can use our ideal gas law. Okay, and in that PV will be equal to constant. So we can say ideal gas law, which is for PV is equal to nRT, and nRT at constant pressure and volume. Therefore we can write that because this R is also a constant, therefore we can write this N multiplied by T will be equal to constant. And we have, you can say this, we can write this particular equation in terms of initial as well as final. Therefore we can say that our N final multiplied by temperature final will be equal to N initial and multiplied by temperature initial. So in terms of a ratio, we can write this as Nf upon Ni will be equal to Ti upon Tf, and initial temperature is our 17 degree. So in terms of Kelvin, that will be 290 and it will be 300. So this ratio comes as 29 upon 30. So from here we can write that our Nf is equal to 29 upon 30 times Ni, and we are supposed to find out Nf minus Ni. Therefore, we substitute value of Nf in terms of Ni, giving us 29 upon 30 minus 1 times Ni. So this gives us minus 1 upon 30 times Ni. And we can also find out our initial number of molecules by using ideal gas law in terms of initial. So we can say initial number of molecules. We can write our ideal gas law, PV is equal to NIR multiplied by TI. From here we can say that our Ni is equal to PV, and this is our R T of I, and P and V are given initially, so this is our 1 into 10 to the power 5, volume is our 30, R we know is our 8.314, and initial temperature is our 290. So we get this Ni is approximately equal to 1.243 into 10 to the power 4 moles. And from here we can find out our number of molecules. So we can say our number of molecules, that is our suppose capital Ni, and that will be equal to number of moles multiplied by the Avogadro's number. So this comes as 1.243 into 10 to the power 4 multiplied by 6.022 into 10 to the power 23. So we get number of molecules initially is equal to 7.485 into 10 to the power 27. And we can easily find out, because this we have to find out Nf minus Ni, which is nothing but our change in number of molecules. Therefore, we can say that change in molecules will be equal to our Nf minus Ni, and that is our 1 upon 30 times Ni, and Ni we just calculated. So we can say this is equal to minus 1 upon 30 times 7.485 into 10 to the power 27. So this comes approximately as minus 2.5 into 10 to the power 26. Sorry, 10 to the power. I think there is some, might be, but answer is option number C. There is some problem in the power of 10, but option C is the correct one. C is correct. Next question. It was asked in the 2018 mains, and it states that the mass of a hydrogen molecule is 3.23 into 10 to the power minus 27 kg if 10 to the power 23 hydrogen molecules strike per second a fixed wall of area 2 cm square at an angle of 45 degree to the normal and rebound elastically with a speed of 10 to the power 3 meter per second. Then the pressure on the wall is nearly. So in this case, we have to find out the pressure. And we know that our pressure is force per unit area, or in terms we can also say that our force is rate of change of momentum. Okay, so we are going to find out rate of change of momentum, and that is going to help us finding the further part. So you can say that pressure is force per unit area, and force is rate of change of momentum. Rate of change of momentum. Okay. So because it is said that the molecules are striking the wall at an angle of 45 degree, so let's find out the, okay, let me draw an approximate figure. Suppose this is the wall and this is the normal, so it is making an angle of 45 degree with the normal. So this is angle of 45 degree, and with the velocity v, therefore we can find out its x component, or we can say horizontal component. So let us call this as v of x. So you can say the initial velocity component normal to the wall. And that will be v of x is equal to 10 raised to power 3 cos of 45. So we get from here that our v of x is equal to 10 raised to power 3 divided by square root of 2. And it says that it bounds elastically. Okay, so from here we can say that after elastic rebound, so after elastic rebound we are going to have the velocity of this hydrogen molecule. Let us suppose that is our Vx prime. Okay, but it will be in the negative direction. So after elastic rebound, we can say that the velocity in x direction, that is Vx prime, will be equal to minus 10 raised to power 3 and square root of 2. Now we can easily find out rate of change of momentum. So you can say momentum change per unit molecule. Momentum change per unit molecule, and let us call this as delta p of x in x direction will be equal to m Vx minus Vx prime, and we know all these values, so we can say our delta p of x will be equal to mass is our 3.32 into 10 raised to power minus 27, and this comes as 10 raised to power 3 divided by square root of 2 minus 10 raised to power 3 square root of 2. And this will be approximately equal to 4.692 into 10 to the power minus 24. Now, like we said, that our force is rate of change of momentum. Therefore, we can say force F will be equal to delta Px. One second. Okay, so we are total number of molecules is 10 to the power 23. Therefore, we can say that the total force, let me write it, total force, so you can say total force, that is our F, will be equal to number of molecules 10 to the power 23, and we have this for rate of change of momentum per unit molecule, and we substitute the value, we get that F is equal to 10 to the power 23 multiplied by 4.692 into 10 to the power minus 24. Okay. And we get this as 0.4692 newtons, and we have to find out the pressure. So pressure is nothing but a force per unit area. So you can say the pressure P will be equal to force oblique area, and we have this as 0.64692, and area is 2 centimeter. So this comes as 2 into 10 to the power minus 4, which gives us approximately 2.346 into 10 to the power 3 pascals. So we get this as 2.35 10 to the power 3 pascals, Newton meter square. So option B will be correct. B is correct. Next question. It was asked in the 2018 mains, and it states that 2 moles of ideal monatomic gas occupies a volume V at 27 degrees centigrade. The gas expands adiabatically to a volume of 2V. Calculate the final temperature of the gas. Second, change in its internal energy. So here we are given monatomic gas. So we know that is gamma ratio is equal to, which is our adiabatic ratio, adiabatic index is 5/3. So we can say for monatomic gas, we have our gamma is equal to 5/3. So let's find out first of all the final temperature. Final temperature, we know for adiabatic process, the product of temperature volume raised power gamma minus 1 is constant. So you can say for adiabatic, process, we have temperature volume gamma minus 1 is equal to constant. So we can write this as our initial temperature, initial volume, gamma minus 1 is equal to final temperature, final volume, gamma minus 1. And from here we can write final temperature will be equal to initial temperature, and we have this as a ratio of our initial volume, final volume, gamma minus 1. Gamma is over 5/3, and all these things are given to us. We simply substitute them. So we get our final temperature is our 300 Kelvin, and we have this as our V upon 2V and 5/3 minus 1. Here this V and V cancels out, so this comes as our 300 1/2, and this will be equal to our 2/3. So approximately you can say it is equal to 189 Kelvin final temperature. Now we come to our change in internal energy. Change in internal energy. So for that we have a standard formula. Delta of U is equal to N C of V multiplied by delta T, and this is monatomic, so C of V is 3/2 times R, and delta T is the difference in temperature. So we can simply substitute the values. We get this as delta of U is equal to 2 3/2, and R is our 8.314, and temperature is our 189 minus 300. So we get this is equal to approximately minus 277 joules. So we get 189, and minus this option D is correct. So we can write this in terms of kilojoule also, 2.7 kilojoules. So we can say option D is correct. Next question. It was asked in 2019 mains, and it states that in a cylinder of radius R is surrounded by a cylindrical shell of inner radius capital R and outer radius 2R. The thermal conductivity of the material of the inner is K1 and that of outer is K2. Assuming no loss of heat, the effective thermal conductivity of the system for heat flowing along the length of the cylinder is. So for this we can just draw an approximate diagram, and so this is our internal one. Okay, basically it will be a coaxial, and this is our external diagram. Sorry, is not according to the scale. And the inner is our radius is our R, and the outer radius is 2R. conductivity is K2 as well as our K1. So we have to find out the effective thermal conductivity, and that is our area weighted average. Okay, that is a, you can say, and we have to remember that the heat is flowing along the length, or we can say heat will be flowing parallelly. Okay, so in this as well as this, so heat flow will be parallel to each other. So we can say for parallel heat flow, along the length the effective thermal conductivity is the area weighted average. Area weighted average. So let's find out the areas. So we can say area is basically cross-sectional area. Okay. So we can say our cross-sectional areas and let us find out for inner cylinder. That is A1 is equal to pi r square, and for the shell that will be equal to our A2, and we have our pi 2r square minus pi r square, and that will be coming as 3 pi r square. Therefore total area A will be equal to A1 plus A2, and we get this as our pi r square plus 3 pi r square is equal to 4 pi r square. And the heat flow suppose is our Q, and that will be equal to our Q1 plus Q2, and the general formula we can write this as Q of I is equal to K of I A of I delta T upon L, where I is our variable, which is for, in this case we have two areas, so this will be Q1 as well as Q2. Therefore we can write that our effective conductivity which is our Q will be equal to K effective A delta T upon L, and we can just revise this equation and we can call this as our, in terms of the respective, we have this as K1 A1 delta T upon L plus K2 A2 delta T upon L, and this will be equal to K effective area delta T upon L, and here this delta T upon L cancels out throughout, therefore we can write this as our K effective area total, that is our K1 A1 plus K2 A2. We simply substitute the areas, we get this as K effective area, total area is our 4 pi r square, and K1 inner area is our pi r square plus K2, and this is our 3 pi r square, and this pi r square cancels out throughout, so we get this as K effective will be equal to, we have K1 plus 3 times K2 upon 4. K1 plus 3 K2, option number B is correct. B is correct. Next question. It states that when m1 gram of ice at minus 10 degrees centigrade, specific heat 0.5 is added to m2 gram of water at 50 degrees centigrade. Finally, no ice is left and the water is at 0 degree centigrade. The value of latent heat of ice is, okay, so in this case, the ice is going to melt from minus 10 to 0 degree centigrade, so its temperature is going to rise, and water is going to come from the 50 degree centigrade to 0 degree centigrade, so we can say that its temperature is going to fall. And obviously, as the water temperature is going to fall, it is going to provide the heat which will be used in the melting of the ice, or simply we can say the heat lost by the water will be equal to heat gained by the ice. Heat lost by the water will be equal to heat gained by the ice. So let's find out the respective heats. So we can see heat to warm the ice, from minus 10 to 0 degree centigrade. Let us call this as Q1 is equal to our M1, and its specific heat, that is 0.5, and the change in temperature. Let me write the formula first. So we have M1, specific heat of our ice, and delta T. So we can say our Q1 will be equal to our M1 ice is given as 0.5 and the temperature is our 0 minus of minus 10, that will be coming as 10. We can write this equal to 5 times m1. And so this was to warm the ice, but it is said that there is no ice left. So it means the ice is going to melt also. Therefore, we can say the heat required to melt the ice. Heat to melt ice. Let us call this as Q2, which will be equal to mass and its latent heat. This latent heat we are supposed to find out. And then we come to the water. So we can say heat released by water from 50 degree to 0 degree centigrade. Let us call this as Q3, which will be equal to mass and its specific heat of water and change in temperature. So we can say our Q3 will be equal to our M2 1, and this comes as a 50. So we can say this equal to 50 times M2. So we simply substitute it in our heat lost by the water is equal to heat gained by the ice. But the heat gained by the ice is a two-step process. First is the warming of the ice, that is Q1, and then is the melt of the ice, that is our Q2. Therefore, we can say that our Q1 plus Q2 is equal to Q3. So we substitute the value, we get this as 5m1 plus m1 times L is equal to 50 times m2. And we are supposed to find out our L, latent heat, will be equal to, this will be our 50m2 minus 5m1 divided by m1. So we can just shift the ratio as per our answer. So this comes as 50 m2 upon m1 minus 5. So we get 50 m1, 50 m2. Option A is correct. A is correct. Next question. It states that a thermally insulated vessel contains 150 grams of water at 0 degree centigrade. Then the air from the vessel is pumped out adiabatically. A fraction of water turns into ice and the rest evaporates at 0 degree centigrade itself. The mass of evaporated water will be closest to, we have given latent heat of vaporization as well as latent heat of fusion of water. So we have to find out the mass of evaporated. Okay. So we are given that we have 150 gram of water and it's turned into ice and rest goes into evaporation. So we can say that we assume that the water that evaporates is suppose our M, and which turns into ice is suppose X. Therefore, according to conservation, this M plus X should be equal to the mass of the water, that is 150 grams. Okay. obviously it says that the process is adiabatically because system is insulated, so we can just use the energy conservation or energy balance. Okay. So first of all, let's find out the heat for evaporation. Heat for evaporation, let us call this as Q evaporation, will be equal to mass and latent heat of vaporization, that is our, one second, specific heat. Latent heat of vaporization, something is missing. Heat for evaporation, yes. So this will be mass into our okay, this is given in kg, so we can say mass into 10 to the power minus 3 times 2 into 10 to the power 6, and this comes as our 2000 times m joules. And then we come to the heat for fusion. Heat for fusion, or we can say ice formation. And let us call this as Q fusion will be equal to, this is X, and latent heat of fusion is given as 3 point, so this will be also 10 to the power minus 3 into 3.36 into 10 to the power 5. So this comes to us as 336 times X joules. Now these two should be equal with each other. Okay. So we can say our energy balance gives us heat for vaporization should be equal to heat of fusion, because the system is entirely insulated, so all the heat that will be used in this entire system will be balanced. So vaporization should be equal to our fusion heat. Therefore we can write that 2000 m will be equal to 336 times X, and from here we can say that our X is equal to 5.952 times m, and we already know that the summation is equal to 150. Therefore we can say that our m plus 5.952 times m is equal to 150, and this comes as our m is equal to 150, and this is 6.925, approximately equal to 21.6 grams. So option B is correct. So you can say this is approximately 20 grams. So option B is correct. Next question. it states that when 100 gram of liquid A at 100 degrees centigrade is added to 50 gram of liquid B at temperature 75 degrees centigrade, the temperature of the mixture becomes 90 degrees centigrade. The temperature of the mixture if 100 gram of liquid A at 100 degrees centigrade is added to 50 gram of liquid B at 50 degrees centigrade, then the temperature of the mixture will be. Okay. So in this case, let us say that the specific heat of A and B is SA and SB. Rest is quite simple because it is based on entirely on only one equation. So we can say specific heat of A is our S of A, and for B it is S of B. So let us, there are two cases. So we can say for first case, we have 100 gram of our 100 gram of liquid A. So this comes as our MA SA delta TA plus MB SP delta TB is equal to 0. In terms of negative we can write it, but in summation it is quite easy to remember. Now we simply substitute the values. So we have this as 100 SA and 100 minus 90 plus 50 SP 75 minus 90 is equal to 0, because this is nothing but based on our conservation. So heat lost by the one will be heat gained by the other. That's the only premise of that. And we can write this as our 1000 SA will be equal to 750 times SP. So we get our SA is equal to 3 by 4 times SP. Now we have a second case. In second case, we have to find out temperature, same formula. So we can say that our mass of A, S of A is 100 minus T plus mass of B, specific heat of B, and we have 50 minus T is equal to 0. We substitute the values. We get this as our 100 into SA is our 3 by 4 times SP, 100 minus T plus 50 SP, and this is our 50 minus T is equal to 0. And obviously SP we can just, it cannot be equal to 0, so we just remove it, and we can write that our this will be 4 and 25. So we are going to have this as 7500 minus 75T plus 2500 minus 50T is equal to 0. So from here we can say that our 10,000 is equal to 125 T, which gives us that the T is equal to 10,000 divided by 25, and this comes as our 80 degree centigrade. So option B is correct. B is correct. Next question. It states that in a process, temperature and volume of 1 mole of an ideal monatomic gas are varied according to relation Vt is equal to K, where K is a constant. In this process, the temperature of the gas is increased by delta T. The amount of the heat absorbed by the gas is, where R is the gas constant. So relationship is given to us. So we are given that our V times T is equal to constant basically. So from here we can say that our T is inversely proportional to our volume V. And from ideal gas equation, we have our PV is equal to nRT, and N is our 1 mole and it's monatomic. Therefore from here we can say that our PV is proportional to temperature T. So in place of temperature T we can substitute 1 upon V. So we get from here PV is proportional to 1 upon V, or we can say that the PV square is equal to constant. Now this equation is nothing but a equation for our polytropic process, whose general equation is our PV raised to power x is equal to constant. Okay. So we can say that this is our polytropic process, which is in general given as PV raised to power x is equal to constant. Therefore, we can say that the value of x is equal to 2. Okay. And we also know another formula for our polytropic process in terms of work done. So we can say work done in a polytropic process is, suppose, delta W, and that will be equal to P2 V2 minus P1 V1 1 minus x, but there is a condition for x not equal to 1. Okay. And if x is equal to 1, we can write the same formula in a different way, is equal to PV natural log of V2 upon V1, and this is when x is equal to 1. Okay. In this case x is equal to 2, so we are going to use our first formula. We can say for x equal to 2, we get delta W is equal to P2 V2 minus P1 V1 upon 1 minus 2. Okay. And we can write this ideal gas, we can say this is equal to over nR we can take as common. So So we get this as T2 minus T1 upon minus of 1, and we get this delta of W is equal to minus NR delta of T, and we are given that we have a monatomic gas, so therefore we can say that internal energy for a monatomic gas, that is standard formula. So we can say that our internal energy for monatomic gas that is delta of U will be equal to 3 by 2 times R and delta of T. Now we can find out heat absorbed by using first law of thermodynamics. So we can say first law of thermodynamics, this gives us delta of Q is equal to delta W plus delta of U, which is our delta of is number of moles is 1, so this comes as minus RT minus R delta of T plus 3 by 2 R delta of T. So we get this as delta of Q is equal to 1 by 2 R times delta of T. So we have this as 1 by 2 R of delta T. Option C is correct. C is correct. Next question. It states that a metal ball of mass 0.1 kg is heated up to 500 degrees centigrade and dropped into a vessel of heat capacity 800 joule per Kelvin containing 0.5 kg of water. The initial temperature of water in the vessel is 30 degrees centigrade. What is the approximate percentage increment in the temperature of the water? Specific heat capacities of water and metal are respectively 4200 and 400. Okay. So in this case, the metal ball is heated, dropped into water, and the water is stored in a vessel. So you can say the heat lost by the metal will be heat gained by the water and vessel, that is energy, heat conservation basically. So you can say heat lost by metal will be equal to heat gained by water plus heat gained by vessel. So we put respectively equations. So we get mass of our metal, specific heat of metal, change in temperature 500 T, and we get this as mass of water, specific heat of water, change in temperature T minus 30 plus heat gained by the vessel and specific heat and T minus 30, and we simply substitute their values. We get this as 0.1, 0.1 multiplied by 400. 500 minus T is equal to 0.5, 4200, and T minus 30 plus 800 T minus 30. Now this is quite easy to solve. We can just write it directly. We are going to get, or let me open it. So we are going to get this as 40, and 40 multiplied by 1 second. So here we can just 20, 20, 20 cancels out, and this comes as I think, okay, let me keep it at this is. So this will be coming as 40 times 500 minus T is equal to, and here we are going to get 1 second. So we have 0.5 multiplied by 200, so we get this as 2100 T minus 30 plus 800 T minus 30, and we get this 40 multiplied by 500, that is 20,000 minus 40T is equal to 2100 T minus, and this will be our 30, and this will be our 3 and 6 plus 800 T minus 30, and this will be 24. Let me check. 0.1 kg specific heat of water is 1 second. Okay, water is 42 this, and metal is 400. Yeah, this is correct. So we can just solve this now, and we get this as our 63,000 plus 24,000 and minus 20,000. 1 second. So we have 21 into 30, and this is plus 24,000 minus 20,000. So we get this is equal to 67,000, and we get this as our 800 minus 40. will be 760 T. So from here we get our T is equal to 67,000 divided by 760, which is 88.15. Okay, and we have to find out the percentage increment. So we can say our percentage increment will be equal to our T minus 30 divided by 30 into 100, and T we found out is our 88.15 minus 30 and divided by 30 into 100. So we get this as minus 30 divided by 30, 19%. I think, let me check it again. 88.15 minus 30 and divided by 30 into 100. I think there is some problem in the calculation. $500. Okay, this is centigrade and this is in Kelvin. Okay, so I have to do this entire thing again. So we have this as our 500 plus 273. This will be over 773 and 273 plus 30, 303. Entire calculation again. Okay, anyways, let us start again. So we have our mass of metal is our, where it is, 0.1. So this comes as 0.1. Specific heat of metal is given to us as 400. This is 773 minus T is equal to, let me take this as 3 minus 303 as common. So we get this as mass of water. Mass of water is 0.5. Specific heat of water is 4200 plus for our vessel is given as 800. Okay, so we get this will be our 40 times 773 minus T is equal to T minus 303, and we get this as 0.5 into 4200 plus 800, that is 2900, and we can say that our 0 and 0 cancels out, divided by, so we get this as 773 minus T is equal to T minus 303, and this will be our 72.5, which can be written as 72.5 times T minus, and we have this as into 303, which is I think, I'm not sure. Okay, let's try it out whether it comes or not. 21,967. So we get this as our, this will be T plus, this will be coming as 73.5 times T is equal to, and this will be over plus 773, which will be 22740. Therefore T will be equal to divided by 73.5, 309. Okay, anyway, it's in Kelvin. 309 Kelvin. So now hopefully we get percentage increment will be equal to, this is our T minus, we have this as 30, that is 303 divided by 303 multiplied by 100. So we get this as 309 minus 303 divided by 303 into 100, and we have this as minus 303 and divided by 303 into 100, 21%, 20%. So we can see approximately this is equal to 20%. So we have our option D is correct. Next question. It states that ice at minus 20 degrees centigrade is added to 50 gram of water at 40 degrees centigrade. When the temperature of the mixture reaches 0 degrees centigrade, it is found that 20 gram of ice is still unmelted. The amount of ice added to the water was close to. Take specific heat of water as 4.2, specific heat of ice is 2.1, and heat of fusion for water at 0 degree centigrade is 334. So in this case, there will be heat lost by the water, and that heat lost will be gained by the ice. And ice is going to gain that heat in the two format. One is reaching the temperature of the ice from minus 20 to 0 degree, and then the melting of the ice at 0 degree centigrade. So first of all, let's find out the heat lost by the water. which is our QW, and that will be equal to our mass of water, and we have this as specific heat of water and delta T. So we get Q of W is equal to 50, everything is grams, so this is 4.2, and it is given in degree centigrade, so this will be 40 minus 0, giving us 8400 joules. And it says that ice is still unmelted, only 20 gram is still unmelted. Okay. So let us say the initial mass of ice is m, initial mass of ice is ever m, therefore we can say that melted ice will be equal to m minus 20. Now we come to the melting of the ice or heat absorbed by the ice, and that will be first will be our heat to warm ice to 0 degree centigrade, and that is suppose our Q1 will be equal to the mass of the ice multiplied by its specific heat of the ice and delta T, and we get this as our Q1 will be equal to mass of the ice is our m, specific heat is given as 2.1, and we have this 20. Okay. So this we get as 42 times m. And then we come to the melting of the ice. So we can say heat to melt ice. Let us suppose that is our Q2 will be equal to this ice melted, that mass of the ice melted. So we can say mass melted multiplied by its latent heat of our ice. So we can say that our Q2 will be equal to m minus 20 and 334. Now we can just put in the heat lost by the water is equal to heat gained by the ice. Therefore you can say, or we can simply term, we can say heat balance. Heat balance. Therefore we can write that our Q1 is equal to QW is equal to Q1 plus Q2, and QW is our 84 is equal to Q1 is our 42 times m plus m minus 20 times 334, and we can write this as our 42m plus 334m minus this will be coming as 0866 is equal to 8400. So this gives us that m is our approximately 40 grams. So option A is correct. Next question. It states that an unknown metal of mass 1 and 2 gram heated to a temperature of 100 degrees centigrade was immersed into a brass calorimeter of mass 128 gram containing 240 gram of water at a temperature of 8.4 degrees centigrade. Calculate the specific heat of unknown metal if the water temperature stabilizes at 21.5 degrees centigrade. Specific heat of brass is 394 joule per kg per Kelvin. So in this case, once again we can say that our heat lost by metal will be equal to heat gained by the water and the calorimeter. So we can say heat lost by water is equal to heat gained by water, heat lost by metal. Heat gained by water and calorimeter. Therefore, we can write mass of metal, specific heat of metal and their change in temperature is equal to mass of water, specific heat of water and its change in temperature plus our mass of brass, specific heat of brass and its change in temperature. So we substitute all the values. This is our 0.192 times Cm and this comes as 78.5 is equal to 0.24 4200 13.1 plus 0.28 and 394 and this comes as 31.1. So this will be our 15.072 C of M is equal to and 13204.8 plus 660.65 which will be equal to 13865.64. So we get our specific heat of metal is equal to 1386564 and 15.072 approximately equal to 920 joules per kg per Kelvin. So approximately it equal to option A is correct. Option A is correct. Next question. It states that uniform cylindrical rod of length L and radius R is made from a material whose Young's modulus of elasticity equals Y. When this rod is heated by temperature T and simultaneously subjected to a net longitudinal compressional force F, its length remains unchanged. The coefficient of volume expansion of the metal of the rod nearly equal to. So in this case, it is basically we can say that the thermal expansion should be equal to the compressive force, or we can say compressive strain, okay, because length is unchanged. So you can say thermal expansion should be balanced by or equal to compressive strain. And our thermal expansion, or we can say our thermal strain, is equal to alpha multiplied by T, and compressive strain is our force oblique area Young's modulus Y. And we also know that our volumetric coefficient expansion, that is our gamma, is equal to 3 times alpha. Okay. And we have to find out, okay, we have to find out gamma. So we can write this as our alpha is equal to F upon area is our pi r square times y times t. So this gives us that the gamma is equal to 3 times F upon pi r square y multiplied by t. So we had this is 3 times F, that is option number C is correct. Next question, we have a 40 degree centigrade, a brass wire of 12 millimeter radius is hung from the ceiling. A small mass M is hung from the free end of the wire. When the wire is cooled down from 40 degree centigrade to 20 degree centigrade, it regains its original length of 0.2 meter. The value of M is close to. Coefficient of linear expansion and Young's modulus of brass are 10 to the power minus 5, 10 to the power 11, and G is said to be given as 10 meter per second square. So because of this decrease in temperature, there will be thermal contraction. Okay. And because of the mass, there will be elongation in the wire. And these two will be balanced by each other, and that is going to solve for our mass M. So we have our thermal contraction, and thermal contraction will result in change in length. So that change in length is about delta L will be equal to the original length, linear coefficient, and change in temperature. So we are given the original length is 0.2, coefficient of expansion is given as 10 to the power minus 5, and the change in temperature is 40 minus 20, that is our 40 minus 20. So we get the change in because of the thermal contraction is equal to 4 into 10 to the power minus 5 meters. Now we are going to have elongation due to mass. Elongation due to mass. Okay, let us suppose that is our M, and so there will be force, or let us suppose that elongation is our delta L, which will be equal to a force L and area into Young's modulus, and this force F will be because of our M into G. So therefore we substitute them, we get this as delta of L is equal to mg times L, and this is A multiplied by Y. So we get that our delta L is equal to M, and G is our 10, change in his origin length is 0.2, and area is our pi 10 to the power minus 6, and Young's modulus is given at 10 to the power 11. So get this as our twice M pi into 10 to the power 5, and the thermal contraction is equal to elongation. You can see that our thermal contraction is equal to elongation. Therefore thermal contraction is our 4 into 10 to the power minus 5, and elongation is our 2 times M pi into 10 to the power 5. So from here we get that our mass M will be equal to is 5 and 5 will 4 pi upon 2, or approximately we can say this is equal to 6.2 kg. I missed 1 second. This is quite simple. I missed something. That's correct. So the closest is we can say is our 9. There is no other option. So option A is correct. It is pretty far. Next question. states that two rods A and B of identical dimensions are at temperature 30 degrees centigrade. If A is heated up to 180 degrees centigrade and B up to T degrees centigrade, then the new lengths are same. If the ratio of their coefficient of linear expansion of A and B is 4:3, then the value of T is. So after heating, it says that length are same. So we can just put the standard formula. We can given that equal lengths after heating. Therefore, we can say that our LA prime will be equal to LB prime. Therefore, in terms of original length, we can say LA 1 plus coefficient of A and temperature is change in temperature 180 minus 30. 180 minus 30 is equal to original length B 1 plus alpha of B, and this is our T minus 30, or we can say this is TB minus 30. So we substitute the values. We are given that after before heating they are also of identical dimensions, so we have our LA is equal to LB. So we can say since LA is equal to LB, so they are going to cancel out each other. So we get 1 plus alpha A 150, 1 plus alpha B, temperature of, sorry, it is mentioned that T, so we can substitute here T minus 30, and this 1 and 1 cancels out. We get this as our alpha A upon alpha B is into 150 is equal to T minus 30. But we are given that their ratio is 4:3. We are given that alpha A upon alpha B is equal to 4/3. Therefore, we get 4/3 times 150 plus 30 is equal to T, and this 150 goes by 50, and we get this as 200. So therefore we get T is equal to 230 degree centigrade. So option A is correct. Next question. It states that two materials having coefficient of thermal conductivity 3K and K, thickness D and 3D respectively, are joined to form a slab as shown in the figure. The temperatures of the outer surfaces are theta 2 and theta 1 respectively, where theta 2 is greater than theta 1. The temperature at the interface is. Basic figure is given to us. We have the thermal conductivity as 3K and K. Their thickness is D and 3D. Outer temperature is theta 2 and theta 1. So we have to find out the temperature of their junction. Let us suppose that is our theta. Okay, so they are in series, so it means the heat flow, or we can say heat flux, is equal. So we know that in series heat flux is equal. So we can say that heat flux for our 1 will be equal to heat flux for our 2. Therefore we can write the standard formula is their conductivity, that is our 3K area, and the temperature difference junction we assumed is our theta. So we get this as theta 2 minus theta divided by their width, which is given as d, and on the other side we have Ka and theta minus theta 1 divided by 3d. So here Ka, D and D cancels out. So we get this as 3 times theta 2 minus 3 times theta is equal to, let me multiply this by 3, is equal to theta minus theta 1, which comes as our 9 theta 2 minus 9 times theta. So we are supposed to find out theta. Therefore we can write that our tan theta will be equal to 9 times theta 2 plus theta 1, giving us that theta is equal to 9 times theta 2 plus theta 1 divided by 10. So option D is correct. Next question. It states that two identical beakers, A and B, contain equal volume of different liquids at 60 degrees centigrade each. Left to cool down, liquid in A has a density of 8 into 10 to the power 2 and specific heat of 2000, while the liquid B has a density of 10 to the power 3 and specific heat of 4000. Which of the following best describes their temperature versus time graph schematically? Assume the emissivity of both the beakers to be same. So in this case, we are basically going to find out the cooling rate, which is the product of their density as well as their specific heat. And from there, we can just find out the rate of change of their temperature. And we start with the equation for cooling rate. So we can say cooling rate, which is also our minus rate of change of temperature, is equal to product of their density as well as their specific heat. So we can say for A, we can write that minus Tt upon T of A will be equal to their density as well as specific heat, which comes as our 800 multiplied by 2000, giving us 1.1 into 10 to the power 6. Similarly, we can write for B. For B, the cooling rate of B is equal to the density of B and its specific heat, and this is our 1000 multiplied by 4000, giving us 4 into 10 to the power 6. Therefore, we can say that our so I can say that my this dB upon CB is greater than their product of CA, and because there is a negative sign associated, so that will be giving us a reverse of this. So this will be dt, rate of change of for our B will be less than rate of change of our A, and which basically means that there will be only difference of slope of both. Okay, so this C and D are not possible. Only possibility is A and B, but we know that the rate of cooling for A is on the higher side as compared to B. Therefore, B and A. So option B is correct. B is correct. Next question. It states that temperature difference of 120 degrees centigrade is maintained between two ends of a uniform rod AB of length 2L. Another bent rod PQ of same cross-sectional area as AB, length 3L by 2, is connected across AB. In a steady state, the temperature difference between P and Q will be close to. A basic figure is given to us. So we are given that we are having a rod AB whose total length is said to be given as 2L. So this total length of AB is our 2L, and we have connected a PQ such that the PQ is our L, and there is another rod which forms some kind of loop, and this length of the rod, that the horizontal one, will be also equal to L, and this vertical will be equal to L by 4, such that total length comes as 3L by 2. And in this case, we are going to draw an analogy between the resistance and with respect to the length. So it means the length we can directly convert into form of a resistance. And for that, we are going to use the standard formula that our resistance is equal to rho L upon A. And it is given that the area of all these cross-sectional areas is equal. Therefore, we can say our resistance is directly proportional to our length. And so we have our total length is 2L. So this AP will be equal to L by 2, and this will be also equal to our L by 2. Okay. So we can say that our AP, which is having a length of L by 2, is going to have a resistance of R by 2. Okay. And similarly, we are going to have PQ. PQ is having a length of L, so we get our resistance of this PQ will be equal to our R. And finally, we are having, let this be a PQ, and let us call this as our R, let us call this as X, and this end as a Y. So we have a px. Px, the length is L by 4. So we can say resistance of our px is equal to R by 4. And we have our xy, length is equal to L. So we can say resistance of our xy is equal to our R. And finally, we are having YQ, whose length is our L by 4. So we can say the resistance of this YQ will be equal to R by 4. So this entire network, we can draw it in the form of the resistances also now. So this is our A, P, Q, X, Y and B. So we have resistance of AP is R by 2, BQ is also our R by 2, and PQ is our R, and we are going to have our XY will be also our R, and here will be R by 4 as well as our R by 4. So we got the resistance network, and we said that temperature difference is 120 degrees centigrade. So for the sake of convenience, we can assume that A is our at 120 degrees centigrade and B is at our 0 degree centigrade. So the difference between the two is 120. Okay, and so let us find out the equivalent resistance rather between P and Q using this loop. So we can say that equivalent resistance across PQ equivalent resistance across PQ, and that is equal to series combination of R plus 4, R plus 4 in parallel with R. Sorry, I'm only finding out across PQ. So all these will be in series. Okay, so I can say across PQ, and this is for our P, X, Y, Q and back to P. So we get this our R across PQ. Let us call this R equivalent across PQ. R equivalent across PQ, which will be equal to R by 4 plus R by 4, and this comes as our 4 plus 2 6, giving us 6R by 4, or we can say 3R by 2. And okay, now the equivalent circuit will be something like this. So we have this as A, P, Q and B, and we have our R by 2, R and R by 2. And here we found out is our equivalent resistance, which is 3R by 2. Now these two resistances, that is this R and 3R by 2, are in parallel. Therefore we can say that our R equivalent will be equal to R, these two in parallel, so we can say this is R parallel 3R by 2, which gives us product of the resistances and their summation. So summation will be equal to 5R, 2 goes by 2, so this is left with our 3R square upon 5R, and this cancels out, so we get this as 3 by 5 times R. So this is the equivalent resistance. Now our circuit comes, this circuit, let me draw it here. So now it will be coming like this. So we have our A, this is our P, Q and B, R by 2, and we found out this is our 3 by 5 times R, and this is our R by 2. So let me draw it again here. So we have our A, P, Q and B, R by 4, R by 4 and 3 by 5 times R. And because all these are in series, so the current will be same. So we can say current in wire AB will be equal to current through PQ. Current through AB will be equal to current through PQ, and current through AB will be our VB minus VA, and we have the total resistance in the circuit is our R by 4 plus 3 by 5 times R plus R by 4, and equal to through PQ is our VQ minus VP, and this is our 3 by 5 times R, and here this R cancels out, and we get that our VB minus VA, and it will be coming as 20 will be LCM, so it will be 5 plus 5 10, and 10 plus 12 22 divided by second, something is, sorry, it is R by 2, my mistake, that's why it's R by 2, R by 2. So this will be coming as now 10, and one, and this will be 8 by 5 directly. So this will be 8 by 5 is equal to VQ minus VP upon 3 upon 5. So this 5 and 5 also goes away, and now it is quite simple. because we know that the current flows because of the potential difference, and heat is going to flow from because of the temperature difference. So in proportionality with respect to temperature, we can write this as our TB minus TA upon 8 is equal to TQ minus TP upon 3, and the difference between TB and TA is given as 120, so we get this as our 128, and this is our 3, and this is our TQ minus TP. Okay. One second. 3/8. Okay. So we get this as 36 by 8, 360 by 8, and so this goes by 4 and 60, and this goes by 15. Therefore TQ minus TP is equal to 45 degree. Okay. So in this case, 45, option A is correct. Next question. It states that a diatomic gas with rigid molecules does 10 joule of work when expanded at constant pressure. What would be the heat energy absorbed by the gas in this process? Okay. So we are work done at a constant pressure is given to us, and we have to find out the heat absorbed. Okay. So we can use our first law of thermodynamics. So we can say that first law of thermodynamics, this gives us that our delta of Q is equal to delta of W plus delta of U, and delta of W is given as our 10, so we have to find out our delta of U, that is our okay. So we are given that work done. We can say that our W is equal to our PdV, or we can say P V2 minus V1, and we can write that our delta W is equal to P2 P1, and in terms of our ideal gas equation, we know that our PV is equal to nRT. Therefore we can write that our delta W is equal to PV2. We can write this as our nRT2 minus nRT1, which gives us nR delta T. Okay, and this W is known to us, so nR okay. So therefore we can write that our this delta Q will be equal to 10 plus, and delta of U we are given, diatomic is there, and okay, so we can write this as our in terms of degree of freedom. Because this is equal to 10. So we can say that our R of T is equal to 1, and we can write this as our NF upon 2 and multiply by R times T, and degree of freedom, because it says a rigid, okay, so this is 10 plus, we have this as 5 by 2, and nRT is also 10, so this goes by 5, and we get this as 10 plus 25. So therefore we get delta of Q is equal to 35 joules. So your option B is correct. So these were the 19 questions. We did 15 questions from 2019, 2 questions from 2018, 2 questions from 2017, and all these questions were from the mains part only. So this completes all the 19 questions. Thank you.